So yesterday we were expanding binomials the long way by physically doing all that, but there is a quicker way if you think about it logically. 1 plus x to the power of n is multiplying 1 plus x n times together, if you like. Now, what we could be saying is, well, what we're going to do is choose a term from each parenthesis. I mean, that's how we multiply, that's how we expand out. So, for instance, if I wanted to find x cubed, I could take x from the first one, 1 from the second, x from the second one, 1 from the third, and so on and so on and so on. But as long as I take x out of 3 of them, I'll end up with x cubed. So how many different ways could I arrange those 3 x's and those n minus 3 1s? And this comes back to our permutations, combinations that we did. So how many ways can we choose 3 x's? Well, NC3. So it's not a coincidence that that coefficient turned out to be the same as we saw with combinations, because that's exactly what we're doing. We're choosing from the 3 parentheses, we're going to pull x out. So that means that we can come up with a generalization. So NCK, yes, we know that represents combinations, but it could also now represent the coefficient of x to the power of k in 1 plus x to the power of k, because we're going to choose x out of k of them. Now, an alternative notation we have when we use binomial theorem, we tend to use it in binomial theorem more than with probability. Probability, we tend to stick with the NCK, and this parentheses notation we tend to use with the binomial theorem. Doesn't mean you have to. I mean, obviously you can interchange. So there's the expansion of 1 plus x to the power of n. NC0 plus NC1x plus NC2x squared, and so on and so on and so on. That, of course, is very limited in its use. So if I had a plus b to the power of n, then NC0, start with the first term to the power of n. Powers of a will go down by 1, powers of b will go up by 1. At any particular time, you can pick a term, those 2 powers should add up to be n. So if I have to expand out 2 plus 3x to the power of 4, I can now just say, okay, well, that's 4c0. Powers of 2 will start at 4, they'll go down by 1. Powers of 3, or 3x, will go up by 1. And then we can tidy that up, and voila! 16 plus 96x plus 216x squared plus 216x cubed and 81x to the 4th. So some nice relationships in Pascal's triangle, and as I said yesterday, this is why we actually call it Pascal's triangle. Not so much that Pascal discovered it, he didn't discover it, but he played a lot with the patterns that could be found inside the triangle. Okay, so what we got here? NCK is n minus 1 CK minus 1 plus n minus 1 CK. That's basically the rule that's allowing us to create the row in Pascal's triangle. It's saying to get a particular term in the nth row, we'd go up to the n minus 1th row and add the 2 immediately above it. I can prove that. So if I've got 1 plus x to the power of n, I could rewrite that as 1 plus x times 1 plus x to the n minus 1. Now the 1 plus x to the n minus 1, I could expand out now using our new idea there. I could say, well, it's going to be n minus 1 c0, c1, and so on and so on and so on. The powers of 1, well, I don't bother writing them down because 1 to the power of anything is 1, of course. But then the powers of x will go up by 1. Somewhere in the middle, there's going to be these 2 terms that are in our theorem that we're trying to prove. There'll be n minus 1 ck minus 1 and n minus 1 ck x to the power of k. So again, if we want to find the coefficient of x to the power of k, then on the left-hand side, we know it's going to be nck out of 1 plus x to the power of n. On the right-hand side, well, the 1 I would multiply by the term that has x to the power of k, and the x I would multiply with the term that has x to the power of k minus 1, and so there we have it. They obviously have to be equal, thus proving our little relationship there. Okay, the second one's about the symmetry of the triangle. So NCK will always equal NCn minus k. So the 2 n1s are equal, go in 1, they're going to be the same, go in 2, they're going to be the same, and so on. I didn't bother with a proof there, but if you remember the formula for NCK, it's n factorial on k factorial n minus k factorial. So there's the symmetry we're looking for. Oh, and the third one simply is that, well, every row starts and finishes with 1 is what that's basically saying. NC naught will equal NCN equals 1. Okay. All right.